Very good. So let's see now where we actually were with all of this. Before we got onto this Dirac delta, here was our expression, right? Psi of x, we see, we're hoping will give us the same thing as this integral. Psi of x prime integrated times 2 pi times m of x prime minus x. So let's see now that we know what m is, how well we are doing. So the question still before us is, do we get psi of x back again if we were to integrate dx prime psi of x prime, and we're integrating from minus infinity to infinity, of now that m of u, which is actually 2 pi times m evaluated at x prime minus x. Because when we had our definition, you will notice we just defined m as being evaluated at that location, x prime minus x. Well, now we have this interesting integral to carry out. One of the first things we realize is that m actually can be replaced with the delta distribution. So maybe I should have written it in terms of the delta distribution originally. And now when we look at this integral, we have to figure out how to handle integrals now with these types of delta functions. Well, notice we've got this new kind of function we're not particularly familiar with maybe yet, but it's written as a function of x prime minus x. So this also cries out for some nice change of variables. So I will define that again as u, and I will rewrite my integral in terms of u. So this integral that I'm hoping will give me psi, I know actually will equal integral, and again, du will be dx prime, so this I can rewrite as du. My limits of integration were out at infinity, so shifting by x isn't going to change that fact. Then I'll have psi. X prime now, from my change in variable, minus x is u, so x prime equals u plus x, or maybe better written x plus u. I have then my delta function of u. And I suppose, really, this 2 pi, it might be nice to bring that out in front of the integral. Okay, so let's then draw a picture of this integral to help us understand what's happening. So the integrand then is the product of these two functions. One is my Dirac delta distribution, centered at 0. So that's this super sharp peak that's very high and very narrow, but happens to integrate to 1. And it's got this very narrow width that is this epsilon factor that we're taking to be smaller than any relevant physical length scale. That's this term. The other term is psi of x plus u. Now here is the crux of the physical argument. The argument is that, in fact, we never have truly, in nature, any discontinuous functions. We may have functions that look discontinuous, right? Here's just a little example. I'll just give you a little thought process here. You might think psi of x is a function, of x, and maybe you think it's moving along, and then suddenly it has a discontinuity, and it jumps up to some other value, and then maybe it decays down. I don't know what shape you have in mind. And you might think it changes instantly from one point of x to another. And certainly mathematical functions can do that kind of a thing. But my argument to you is that physically, such discontinuities don't exist. Physically, my argument to you is that they are just idealizations, just like a point charge is an idealization. An actual function of psi that you might think looks like this, I would argue, at some tiny scale is smooth, right? Like so. I'm trying to draw it. It's very hard to draw. Right? I can make it actually smooth and continuous. But if I make that discontinuity on a scale that is below any physically relevant scale, like a scale over a Planck length, right, you would never know whether or not psi is truly discontinuous, or if I can or is just simply replaced by a nice continuous function. You could never tell the difference between those two situations because we cannot fundamentally resolve things on the Planck scale. That being the case, psi of x I'm saying is going to be always continuous, right? And it's going to be continuous on scales. It may not look continuous at our macroscopic scale or even at an atomic length scale, but fundamentally at the Dirac, the Planck length scale, it is. So psi of x then, so this is my picture of my delta distribution on my plot. My other term in my integrand then is going to look very smooth as this function, psi of x plus u, when viewed on this scale where I could actually see the width of my peak. Now, the next piece of my argument is to notice that, okay, outside the peak, right, outside this range, it doesn't matter what the value of psi is because it's being multiplied in my integrand by this function here that's essentially 0. So I only really have to concern myself with the value of psi in this tiny region that goes across my peak. And if you look at it, you will notice, because psi is continuous, and I can make epsilon as small as I want over this scale, right? Over, say, we can imagine this Planck type scale, psi isn't changing. It's only this little piece that's relevant. I could replace that psi over that tiny scale with a constant function, right? And of course, I could let that constant function be constant even outside the range of the delta. And what I want you to realize is that if I take psi of x plus u, remember x here is a constant on my plot, and just replace it with psi of x, namely replacing it with this constant value, outside of the Dirac distribution, of course, I still get 0, so it doesn't change any contributions outside. And inside, it's essentially the same function. So I can make this replacement and still not change the value of my integral. So that's going to be my plan then. I'm going to replace this psi of x plus u to an extremely good approximation with just psi of x. But now that it's been replaced with psi of x, what I hope you will notice is psi of x now is constant. I can treat it as constant for the purposes, at least, of this integral, because it doesn't change it doesn't change much in value across the relevant region of space, which goes across that distribution. So then I can pull this as a constant out of my integral, and I'm left then with 2 pi times psi of x times the integral from minus infinity to infinity over u of my delta distribution. And the beauty is, we know that this integral, we've just proved it, right? That integral, in fact, here was the answer for that. That integral is, in fact, just 1. So we can see we've basically done it. We were hoping we would get psi of x back again. We didn't. We're off by some constant factor, this 2 pi. But I had warned you all that we were dealing with some unknown proportionality constants. So this isn't really too depressing. And actually, we can take care of the 2 pi. We can just patch things up a little bit. But before I patch them up, I just wanted to give you another math lesson. Right, and this lesson has to deal with for integrals containing delta functions, or delta distributions. When you're dealing with such an integral, what you can do is you can replace the smooth parts, and by the smooth parts, I'm talking about the parts that don't have anything to do with the delta function, but the other parts, such as this smooth part, this wave function, we can replace the smooth parts with constant values. And now, which constant should we choose? So we replace them with constant values. The values we should choose are equal to their value at the location of the peak in that delta distribution. Very important lesson for dealing with these types of distributions. Very good. Now, we are ready to begin to think about what we should do with this factor of 2 pi.